The general electronic configuration of p-block elements is written as ns²np1-6. This configuration is one of the most important concepts for understanding the position, structure, and chemical behavior of p-block elements in the periodic table. The p-block consists of groups 13 to 18, and the main reason these elements are placed in the p-block is that the differentiating, or last added, electron enters a p-subshell. The general configuration ns²np1-6 tells us exactly how the electrons are arranged in the outermost shell of these elements. Let us first understand what the letter N means in this configuration. The letter N represents the principal quantum number, which identifies the main energy level or shell in which the valence electrons are present. For example, in the second period, N has a value of 2, so the outer configuration of p-block elements contains 2s and 2 p-subshells. In the third period, N has a value of 3, so the configuration contains 3s and 3 p-subshells. As we move down the periodic table, the value of N increases because a new principal shell is added. The S2 part of the configuration means that the outermost s-subshell contains 2 electrons. An s-subshell contains only one orbital, and one orbital can accommodate a maximum of 2 electrons with opposite spins. Therefore, the s-subshell, represented by S2, is completely filled. The P1 to P6 part tells us that the p-subshell contains anywhere from 1 to 6 electrons. Since a p-subshell consists of 3 orbitals, and each orbital can hold 2 electrons, the maximum capacity of a p-subshell is 6 electrons. The 3 p orbitals are called px, py, and pz. They have similar shapes but point in different directions in three-dimensional space. The px orbital is oriented along the x-axis, the py orbital along the y-axis, and the pz orbital along the z-axis. Each of these orbitals can accommodate a maximum of 2 electrons. Therefore, 3 p orbitals multiplied by 2 electrons per orbital gives a total capacity of 6 electrons. This is the fundamental reason why the p-block contains 6 groups, from group 13 to group 18. The filling of the p-subshell takes place progressively. The first p-block group, group 13, has 1 electron in the p-subshell, so its general configuration is ns²np1. When we move to group 14, 1 additional electron is added to the p-subshell, giving ns²np2. Group 15 has ns²np3. Group 16 has ns²np4. Group 17 has ns²np5. Finally, group 18 has ns²np6. In this way, the number of p electrons increases step by step from 1 to 6 as we move across the p-block. The first example is group 13. Its general configuration is ns²np1. This means that there are 2 electrons in the outer s-subshell and 1 electron in the outer p-subshell. Therefore, group 13 elements generally have 3 valence electrons: boron, aluminium, gallium, indium, thallium, and nihonium belong to this group. The important point here is that the differentiating electron enters a p orbital, which is why group 13 belongs to the p-block. When we move to group 14, the configuration becomes ns²np2. There are now 2 electrons in the p-subshell. Carbon is the most important example of this group. Its outer electronic configuration is 2s2, 2p2. Silicon, germanium, tin, lead, and flerovium also belong to group 14. These elements generally have 4 valence electrons because the 2 electrons in the s-subshell are joined by 2 electrons in the p-subshell. Group 15 has the configuration ns²np3. At this stage, all 3 p orbitals contain 1 electron each. This arrangement is particularly important because, according to Hund's rule, electrons occupy separate orbitals with parallel spins before pairing begins. Nitrogen provides an excellent example. Its valence configuration is 2s2, 2p3. The three p electrons occupy the px, py, and pz orbitals individually. Therefore, group 15 elements have 5 valence electrons in total. When the fourth electron enters the p-subshell, pairing begins. This gives group 16 the configuration ns²np². One of the three p orbitals now contains a pair of electrons, while the other two contain one electron each. Oxygen is a familiar example with the valence configuration 2s2, 2p4. This arrangement helps explain why oxygen tends to gain or share 2 electrons during chemical bonding. Group 17 has the configuration ns²np². At this stage, 2 of the p orbitals contain electron pairs, and the remaining p orbital contains 1 unpaired electron. Fluorine is an example with the configuration 2s2, 2p5. Because only 1 more electron is required to complete the p-subshell, group 17 elements have a strong tendency to gain 1 electron or share 1 electron in chemical bonding. This is one of the main reasons why halogens are highly reactive. Group 18 represents the final stage of p-subshell filling. Its general configuration is ns²np². Here, all 3 p orbitals are completely filled, with 2 electrons in each orbital. Neon is a typical example, with the configuration 2s2, 2p6. Argon has 3s2, 3p6. Because the outer shell is completely filled, noble gases generally have highly stable electronic configurations and comparatively low chemical reactivity. The relationship between group number and p electrons is therefore very simple. Group 13 corresponds to p1, Group 14 corresponds to p2, Group 15 corresponds to p3, Group 16 corresponds to p4, Group 17 corresponds to p5, and Group 18 corresponds to p6. If you remember this sequence, you can quickly determine the general electronic configuration of any main group p block element. It is also important to understand why the p block begins with Group 13 rather than Group 1. Groups 1 and 2 belong to the s block because their differentiating electrons enter an s-subshell. The d block occupies groups 3 to 12 because the differentiating electrons enter d subshells. After these blocks, the p-subshell begins to fill, producing groups 13 to 18. Therefore, the periodic table can be understood as a systematic arrangement based on which subshell receives the differentiating electron. For example, consider the second period. Boron has the configuration 2s2, 2p1. Carbon has 2s2, 2p2. Nitrogen has 2s2, 2p3. Oxygen has 2s2, 2p4. Fluorine has 2s2, 2p5. Neon has 2s2, 2p6. Notice how the 2s electrons remain constant throughout this sequence while the number of p electrons increases from 1 to 6. This is exactly what the general configuration ns²np1–6 represents. The same pattern can be seen in the third period. Aluminium has 3s2, 3p1. Silicon has 3s2, 3p2. Phosphorus has 3s2, 3p3. Sulfur has 3s2, 3p4. Chlorine has 3s2, 3p5. Argon has 3s2, 3p6. Again, the s-subshell remains completely filled with 2 electrons, while the p-subshell is progressively filled from 1 electron to 6 electrons. There is one important exception that must be remembered, and that is helium. Helium is placed in group 18 because it behaves as a noble gas and has a completely filled first electron shell. However, its actual electronic configuration is 1s2. It does not have a p electron at all, because the first shell contains only the s-subshell. Therefore, helium is a special case. It is positioned with the noble gases in group 18 because of its chemical properties and stable filled shell, even though its actual configuration does not follow the usual p-block configuration ns²np². The configuration ns²np1 to 6 also helps us understand the number of valence electrons in p-block elements. Group 13 elements generally have 3 valence electrons, Group 14 elements have 4, Group 15 elements have 5, Group 16 elements have 6, Group 17 elements have 7, and Group 18 elements have 8, except helium, which has only 2 electrons in its first shell. Therefore, across the p-block, the total number of valence electrons generally increases from 3 to 8. This gradual increase in valence electrons is responsible for many periodic trends. As we move from Group 13 to Group 18 across a period, the effective nuclear charge generally increases. Atomic size tends to decrease. Ionization energy generally increases. And electronegativity generally increases. At the same time, metallic character generally decreases and non-metallic character increases. The electronic configuration provides the fundamental explanation for these changes. The number of p electrons also influences chemical reactivity. Elements with 1, 2, or 3 p electrons may tend to lose, share, or rearrange electrons to achieve a more stable configuration. Elements with 5 p electrons are only 1 electron away from completing the p-subshell, so they commonly tend to gain or share 1 electron. Elements with 6 p electrons have a completely filled p-subshell and generally show much lower chemical reactivity, especially in the case of noble gases. Another important concept is the distinction between a partially filled and completely filled p-subshell. A P1, P2, P3, P4, or P5 configuration represents a partially filled p-subshell. In contrast, P6 represents a completely filled p-subshell. A completely filled p-subshell is associated with a particularly stable electronic arrangement. This is why the noble gases at the end of each relevant period have exceptionally stable outer configurations. The configuration also allows us to identify the group of a p-block element when its valence shell configuration is given. If the configuration ends in np1, the element belongs to group 13. If it ends in np2, it belongs to group 14. If it ends in np3, it belongs to group 15. If it ends in np4, it belongs to group 16. If it ends in np5, it belongs to group 17. And if it ends in np6, it belongs to group 18, with helium again treated as a special case. For example, suppose an element has the outer configuration 4s2, 4p3. The p-subshell contains 3 electrons, so this element belongs to group 15. If another element has an outer configuration 3s2, 3p5, it belongs to group 17. If an element has 5s2, 5p2, it belongs to group 14. This method is extremely useful in chemistry examinations because the valence shell configuration can directly reveal the group of a p-block element. The p-block configuration is therefore much more than a formula to memorize. The expression ns²np1 to 6 tells us the principal shell involved, the completely filled subshell, the progressive filling of the p-subshell, the number of valence electrons, the position of the element within the p-block, and many aspects of its chemical behavior. Once this configuration is understood, the arrangement of groups 13 to 18 becomes much easier to remember. In the simplest possible way, think of the p-block as a 6-step electron filling sequence. The s-subshell is already filled with 2 electrons, and then the p-subshell begins receiving electrons. The first step is P1, corresponding to group 13. The second is P2, corresponding to group 14. The third is P3, corresponding to group 15. The fourth is P4, corresponding to group 16. The fifth is P5, corresponding to group 17. The sixth and final step is P6, corresponding to group 18. Once all 6 p electron positions are filled, the p-subshell is complete. Therefore, whenever you see the expression ns²np1 to 6, remember that n represents the principal energy level, s2 represents 2 electrons in a completely filled s-subshell. and p1 to 6 represents the progressive filling of the 3 p orbitals. Since 3 p orbitals can accommodate a maximum of 6 electrons, there are 6 p block groups, from group 13 through group 18. This single electronic configuration is the foundation for understanding the position, group classification, valence electrons, periodic trends, reactivity, and chemical properties of the p block elements.